In this fifth video lecture, we will learn about group differences, effect size, and meta-analysis. Part 1 looks at group differences, which I will introduce by describing the graphic in front of you. You can see that there are two groups, two distributions, a control group and a psychotherapy group. If these two curves, these two groups, are normally distributed, and the means of the two groups are far enough apart that the difference between means is unlikely to occur by chance alone, we can say that there are significant differences between the two groups. For whatever variable we are measuring, this is true. For example, depressive symptoms or calories consumed during the day or hours of sleep per night, so long as we have a normally distributed sample for both samples, we can compare them and determine whether or not significant differences exist. So this is useful in research because we want to ascertain if there are differences between, say, people who receive CBT to people who don't, and who get some other treatment. We want to know, are they less depressed, for example? In order to determine whether these differences exist, t-tests are statistical procedures that can be used for determining whether a group's mean is statistically different from another group's mean. We may well look at the means and determine that there's a difference, but we want to know how likely is it that that difference is occurring by chance alone. If we have a treatment and a control group, we can determine whether the independent variable, so for example CBT, had an effect on the dependent variable, let's say depression, compared to no independent variable or no CBT. If this difference is statistically different, we can claim causation because, especially if you have a study in which participants are randomized into one of, say, two groups, and if there is a control group comparison like a waitlist, we are trying to eliminate or reduce the impact of confounding or third variables, and this, what's called control, helps us to establish causation because there are less impacts on why we are finding that significant difference between the groups. T-tests can be run for both between group designs, so for example CBT versus a placebo, or within group designs, for example pre versus post. So between group t-tests are also called independent or unpaired t-tests, and within group t-tests are known as dependent or paired t-tests. A within group t-test might be, for example, looking at pre and post scores like we've mentioned above. Here are some examples of between group designs and within group designs. First, between group designs. This one is for independent or unpaired means. So here we have in the intervention group CBT, and in the non-intervention group, the control group, we have waitlist, basically no CBT, and the dependent variable is the same in both cases, depression scores on the Beck Depression Inventory. In our within group design example, we have, also known as, by the way, dependent or unpaired means, we have an intervention group, so CBT, that is used twice. There are two measurements being taken at pre and at post treatment for the same dependent variable, depression scores. Note that when you do this, this is a quasi-experimental design, not a true experiment, because you have the same sample being measured twice, meaning you're not able to randomize people into one of two groups. And that lack of randomization, also lack of control, does not permit you to have a true experiment. This is a quasi-experimental design. In order to understand what the meaning of the t-statistic is, we have to first understand degrees of freedom. The values of a t-test are determined by degrees of freedom, which very much is influenced by sample size. Basically, you have the size of a sample, and that influences the kinds of statistics that you can get, because especially with a t-statistic, we're looking at means and also standard deviations, and the larger sample size that you have, the less impact you have of things like outliers on the standard deviation, say, and that's going to impact the differences you find between groups because, of course, the more impact of outliers, the less you're going to resemble the normal curve. It goes back to our general theory that the bigger the sample size, the more likely you are to emulate the normal curve or the normal distribution, and thus degrees of freedom is basically another way of controlling for that, to make sure that your statistics are looking at whether or not you're following the normal distribution or not. If the t-value is large enough, it becomes unlikely to occur by error alone. In other words, it's unlikely that we would find that finding, the difference between means, just by chance alone. These differences are called statistically significant. That's a specific term that's used, which basically means that there's less than, say, 5% error rate or likelihood of error, of that finding being just chance or error rather than actually existing, and is usually written as one of the following examples. One is a two-tailed example, one is a one-tailed example, which, as you'll recall from a prior video lecture, the two-tailed and one-tailed pertains to whether or not you're looking at both sides of the curve or one side of the curve. In other words, do you have a directional or a non-directional hypothesis? The first series of numbers reads t in brackets 33 equals 5.65 with a p of less than 0.05 two-tailed. This sounds like another language, I'm sure. What that means is that your t-statistic has a degrees of freedom, which is in the brackets, of 33. Again, that's very much influenced by a sample size. And that the t-statistic is 5.65. Well, what does that mean? Not a whole lot at this point. We don't really know how to interpret 5.65 without understanding how likely it was that we get that number by chance alone. And the next statistic we get is the probability value, or p-value, and that's what really helps us understand the 5.65. For every t-value, at 5.65, 4.97, whatever it is, there is a probability value based on degrees of freedom, the likelihood that you would get that value just by chance. So 5.65 at 33 degrees of freedom is less than 0.05 or 5% likely to happen just by chance or error alone, meaning it's a significant result. It's two-tailed in that we're looking at both sides of the curve. So, for example, if we were conducting a study into whether or not people were happier as home buyers or as non-home buyers, people who rented, and we may hypothesize that we're not really sure, because if you are a home buyer, you may be happier because you own your own property, for example, and are building towards something, you have more equity. Whereas if you are a renter, you may be more happy just because you don't have as many things to upkeep, things to take care of, expenses going out. So we may be unclear about whether or not someone would be happier if they are home buyers or not. And if that's the case, we could have a genuine two-tailed test, because we're not sure whether happiness is going to be higher or lower among homeowners. Okay. I will add that two-tailed tests are quite uncommon in counseling research, and that's because a lot of the time it is actually unethical to use two-tailed tests in a counseling study. You can't really tell an ethics review board, for example, well, people who get CBT might feel more depressed or they might feel less depressed. I just don't know. It's hard to substantiate that. So a lot of the time you have instead one-tailed tests, because you already are going into your study with a hypothesis that, say, CBT is actually going to reduce symptoms of depression. So again, T of 33 in our second line, if you will, our second example, which means, again, we have 33 degrees of freedom for our t-statistic, influenced by sample size, gives us a statistic of 5.98 with a p-value of less than 0.01. And remember, we can have 0.01 as our criterion if we have a one-tailed test. And that's a significant result at less than 1% likelihood of occurring by error alone. Now, I'll just add that you would find those statistics for the same sample set, the same data set sometimes, because one-tailed tests contain less error than a two-tailed test, and so therefore you typically have either larger t-statistics No, you do. You have larger t-statistics and lower error rates just because you're not looking at both sides of the curve. And because you have more of a, say, direction to the research you're doing less data mining, and that just is associated with less error. So one-tailed tests have less error than two-tailed tests, just as an aside. So we've learned about t-tests. I want to introduce you to chi-square tests, which, if you understand t-tests, are not a huge leap. These are used similarly to t-tests in that they are used to determine whether one group's mean is statistically different from another group's mean. Chi-square tests are used when t-tests cannot be performed because the data do not resemble a normal distribution. Remember, you really need to have both of your samples following the normal distribution to be able to use t-tests properly. So when the groups are nominal, for example, when you have men and women rather than string variables, for example, scores on a depression instrument, you tend to have non-normally distributed data. And that is because if you just think about a graph, I want just to visualize this graph, okay? If you have an amount of men and an amount of women, there are only two potential data points you have there. You do not have the potential for 30 or 50 different data points if you just have a categorical men or women variable. That's also known as a nominal variable. And so there's no way you're going to have the normal curve there because you only have two potential data points. You need probably, I don't know, 30, 50 data points, or at least 10 at the very least, to have the possibility of emulating the normal curve. So that is why the more restricted your scale is, the lesser chance you have of getting a normal curve, and the more you're going to rely on chi-square tests. In addition, you may have a sample which is too small for either of the two groups. If you have a sample of less than 30, this often occurs, you do not emulate the normal distribution. Your sample doesn't, and therefore you need to use chi-square, because if you aren't emulating the normal distribution, you really can't use t-statistics, because the whole point of t-statistics is to make inferences from the sample to the population. And remember, the population is theorized to follow the normal distribution, so you don't have a comparison there if you don't have a sample that follows the normal distribution. Just to summarize this in the next bullet, when the latter occurs, so when you have a sample size that's too small, or groups that are not string, you're not using a string scaling method, instead you're using categorical or nominal variables, we cannot make reliable comparisons to the population and thus cannot generalize findings, and we therefore use chi-square. So we learned about t-tests and group differences, as well as chi-square. And next we're going to be learning about effect size. So in other words, we've just been introduced to statistical significance, and now we're going to learn about effect size, which is a very important term and is quite different from statistical significance, or the p-value, the probability value. You see in the graph in front of you what an effect size is. Remember that when you conduct a t-test or a chi-square test and you get a probability value, it's useful in that we know how likely you are to find those differences by chance alone. What it is not useful for is understanding how large those differences are. For example, we don't really know what a big t statistic is. There's no big versus medium versus small t statistic because it's really influenced by sample size. To understand how large those differences are, we use effect size. Here's a very simplistic explanation of how effect size works using the graphic in front of you. We have here a control mean and an experimental mean. Let's say that we have, going back to our prior example, CBT versus waitlist for depression symptoms. Okay. Let's say that our experimental mean is quite different than our control mean. We look at the difference of means, that's on the x-axis just below the figure. You see 70, which is the experimental mean, versus minus 50, which is the control mean, equals 20. And then we have, for the control mean, looking at the standard deviation. You could use the experimental mean for this. Remember, both of those curves look very similar because they emulate the normal distribution. Therefore, you can take standard deviation from either of them and you'll be fairly comfortable. A lot of studies will use what's called pooled standard deviation as the statistic, meaning they will look at the standard deviation for both data sets and use those as the comparison there. So anyway, the standard deviation is 50, which is the mean, minus 40, which is, I guess, one standard deviation away from the mean, and that gives you 10. So the effect size is difference of means, which is 20, divided by the standard deviation, which is one standard deviation is about 10 units, we've decided, apparently, which gives you an effect size of 2. And we'll explore what exactly that 2 number means as we go forward. So before we understand what the 2 means, we have to understand the importance of 2. I'm trying to articulate this to you. In the APA publication manual, it describes this quite well, why we need to have this effect size. It says, for the reader to appreciate the magnitude or importance of a study's findings, it is almost always necessary to include some measure of effect size, because whether or not something is statistically significant really depends more on sample size, and we want to understand how important or large that finding is. That's why we need effect size. So let's return to our between group design to understand what that 2 means, what that effect size means. Let's say we have again our intervention group CBT versus a waitlist control. We're looking at depression scores on the Beck Depression Inventory as our dependent variable. Even if we can determine that CBT, which is the independent variable, caused change in Beck Depression Inventory scores, the dependent variable, compared to a waitlist, that's no independent variable basically, it is unlikely that 100% of the reason for the change in Beck Depression Inventory scores can be attributed solely to CBT. There's probably other variables that are playing into this. So we want to know what is the impact of just CBT, nothing else. Put another way, regardless of whether a t-test might be significant, the amount of what's called variance attributed to the model, or, in other words, size of the effect, might be very small or very large. Because remember, statistics, t-statistics are influenced by sample size. So we have 4 boxes in front of you, and these help us understand how effect size is useful to us. We have in each of the boxes 2 curves. Okay, you will see as the boxes continue, as the D statistic increases, that the curves are further and further apart. So D equals 0.5, those curves are fairly close together. D equals 1, those curves are moving further apart. D equals 2, even further. D equals 3, even further still. So to surmise, the larger what's called the D statistic, or the effect size, this is known as Cohens D. We're going to explain what that is in just a moment. The larger that is, the further apart those groups are, meaning the larger the difference between groups. So, I mentioned the word, or the letter I should say, D. So what is D? Well, Cohens D is a statistic used to compute effect size for t-tests, and it uses the following guidelines. A small effect is 0.2, a medium-sized effect is 0.5, and a large effect is 0.8. So in the graphs we just looked at, anything above 0.8, so 1, 2, and 3 are quite large-sized effects. 0.8 is the size for large effects. So just to practice, D equals 0.37 is a small to medium-sized effect. D equals 0.62 is a medium to large-sized effect. And D equals 2.11 is a very large-sized effect. Here's a table that helps us understand the various what are called parameters to effect size. You will notice if you scroll down the first column, the left column, and you get to Cohens D. The use is for t-tests, and it gives us our 0.2, 0.5, and 0.8 in terms of small, medium, and large. Some of the other effect sizes that are useful for you to know about include Pearson's R. That's our very first effect size on the just below the main column heading, and this is used for correlation and has 0.1, 0.3, and 0.5 for small, medium, and large sized effects. Notice that the parameters are different for Pearson's R compared to Cohens D. Every effect size has different parameters, so you need to know the actual effect size parameters when you're interpreting it. For example, 0.3 means something very different in Cohens D than it does in Pearson's R. Okay. Then next we have another important one, which is eta squared. This is used for analysis of variance or ANOVA, and there are different parameters depending on what type of eta squared statistic you're using. If you're using a one-way ANOVA, it's known as a regression, for example, that is smaller than if you're doing just a typical kind of ANOVA test. And you'll notice that those numbers are even smaller still than Pearson's R. So not that those numbers are, that if you get a, say, 0.06 effect size using one-way ANOVA, that's not a small-sized effect, it's a medium-sized effect, and you need to know the parameters to interpret that fully. Those are the main ones that you're probably going to come across in research studies: D, R, and then eta squared. So we've kind of explained effect size. Now we're going to look at how to understand statistical language. You'll see here that there is an example statement from a study about youth mentoring that uses some statistical language that we're going to interpret. It says, youth being mentored ranged in age from 14 to 19, and it gives us a mean and a standard deviation. M equals 15.37, SD equals 1.15. So this is how we would interpret that. The youth in the study ranged in age from 14 to 19. The average age, the mean age of youth in the study, was around 15 years old, a little bit older, and there was a standard deviation of 1.15. Now this is how you interpret that. Remember, 1.15, if you're looking at what percentage of people are going to be reporting that, if you minus 1.15 from 15.37, you get somewhere around 14, and if you add 1.15 to 15.37, you get somewhere around 16.5. So 68%, that's one standard deviation plus and below the mean, are between the ages of 14 to 16.5. And if you take away and add another standard deviation, that gives us 95%. That's two standard deviations above and below the mean. So 14 minus 1.15 again is going to be something around 13 or approaching 13. And if you add 16.5 plus 1.15 again, you get right around 17.5, just above that. So I'm just briefly describing to you how you do this, but we can interpret that 95% of youth in the study were between the ages of 13 to 17.5. I hope that makes sense to you, that you can use standard deviation to understand where the majority of people fall in terms of that mean. So that's understanding descriptive statistics. Next, we're going to understand inferential statistics. This is where we get into our T and P and D. Here's an example statement from a study comparing two note-taking interventions. These were students who received partial graphic organizers compared to complete graphic organizers. Students who received the partial graphic organizer notes, and it gives us a mean of 138.62 with a standard deviation of 11.94, scored higher on the quizzes than did students who received the complete graphic organizer notes. Again, it gives us a mean of 133.13, standard deviation of 12.40. Let's stop there. We can see that there's only a slight difference in standard deviation, but there is quite a large difference in mean, or at least somewhat of a large difference, 138 versus 133. So we may anticipate that there's going to be some difference there between means. especially because the standard deviations are comparable. And remember, the t-test, it really depends on things like following the normal distribution and having similar sample groups. So that's good that the standard deviations are similar. The t-statistic has degrees of freedom of 112. This is the statistical test with degrees of freedom related to the number of participants. It's not exactly the number of participants, but it's basically telling us that there are quite a lot of people in this study. And remember, the higher the degrees of freedom, the better. So there are probably more than 100 people in this study based on the degrees of freedom. It gives us a value of the t-statistic, which is 2.41, and a probability value of the statistical test, which is p of less than 0.05. Remember, the 2.41 doesn't mean much without looking at the probability statistic, and we know that the 2.41 is less than 5% likely to happen by chance alone. So it's significant, which is good. That still doesn't tell us how big that difference is. Next we need Cohens D. This is the value of the effect size, and next we get a D statistic of 0.45, which, as you know from what we've just discussed, this approaches a medium-sized effect. So that's a pretty decent-sized effect. So there do seem to be differences between students who received partial graphic organizer notes compared to students who received complete graphic organizer notes, and those who received the partial notes actually performed better on the quizzes than those who received the full whack, the complete graphic organizer notes. That's how we would interpret that kind of statistical language. Next we're going to learn about meta-analysis. We learned about group differences, including t-test and chi-square. We learned about effect size, and now we're going to learn about meta-analysis. As you can see from the graphic in front of you, meta-analysis is all about understanding the combined impact, or also known as pooled, P-O-O-L-E-D, pooled impact of multiple studies to determine how much of an impact the overall treatment has, or the overall approach, or whatever it is that you're measuring. So, for example, if we had multiple studies that looked at CBT and its impact on depression symptoms compared to a waitlist, we had 1, 2, 3, 4 studies that did this, that investigated this. We would want to know the impact combined for each of those studies. And so it gives us one statistic for all of those studies that helps us understand, okay, what is really going on here and how big are those differences really across multiple studies. This tends to have more weight in the research community, meta-analysis does. This is because meta-analysis is the pinnacle of empirical research. It combines multiple studies to give us one overall impact rating, which is really useful. Effect size allows us to do this, to do meta-analysis. And if you recall from what we discussed earlier about evidence-based practice, meta-analysis is at the very top of the hierarchy or the pyramid in terms of what we value most out of research studies, followed by randomized control trials or true experiments, where we have essentially randomization and control. Meta-analyses pull together the results of individual quantitative experiments for the effect of the IV compared to control groups and compute overall effect sizes. This just summarizes what I just shared with you. Whereas effect size is often delineated by D, effect size for meta-analysis is typically indicated by D+. All that D+ means is just another statistical language term that means that we have multiple studies being combined to give us this overall effect size, rather than just one study. So why is meta-analysis useful? Well, let's look at what happened in the history of counseling and psychotherapy. In 1977, Smith and Glass, and Jean Glass is pictured there, found that psychotherapy was more effective than no intervention in 75% of cases, thanks to meta-analysis. And that was at a time when psychotherapy was coming under attack for being ineffective, not very useful, too expensive. And so the fact that researchers found that 75% of people actually get better compared to not receiving psychotherapy at all was a very important finding and validated the field. Thank you, Gene Glass. About 20 years later, Bruce Wampold's meta-analyses determined that effective treatments, or quote effective treatments, such as CBT, are only marginally more effective than other interventions once controlling or confounding variables have been controlled for. Once confounding variables have been controlled for. So, for example, allegiance bias. Allegiance bias occurs when the theorist is also the researcher. And unfortunately, as you can imagine, when you're researching your own theory, you tend to want to find significant findings that favor your theory, and that is called allegiance bias and is misleading. And so when you take out studies from a meta-analysis that have the theorist as the researcher and just leave studies that are done by independent researchers, they have found, Wampold has found, that there really aren't differences between treatment approaches. That treatment approaches aren't that much more effective than others for the treatment of mental disorders. This kind of came as a wake-up call to the counseling community, but we tend to want to avoid that still and want to continue to try to propose that one intervention or treatment is more effective than another. Wampold's finding substantiates something that Saul Rosenzweig articulated very early in 1936. He used the famous Alice in Wonderland story to explain why it was silly for schools of counseling to compare themselves with one another and try to vindicate one another, meaning try to say that one is more effective than the other. He said that in the famous story by Lewis Carroll, you have a bunch of characters who are meant to be running in this race, and as is the case with a lot of the happenings in Alice in Wonderland, something quite strange happens. All of the contestants just run all over the place. They just run in circles, or they run off the track. They don't reach the finish line. And so in response to that, the dodo bird, who's meant to be the judge of this race, says, "All have won and must have prizes." It's kind of an absurd story, but Rosenzweig's point was that really what we need to do is say that all therapies, all approaches, all theories need to be respected and need to be considered effective for the treatment of any mental disorders, really, because there's no real evidence that one treatment is more effective than another for a specific disorder. This is known as the specificity argument. So that was Rosenzweig's articulation in 36, and essentially, 60 years later, Bruce Wampold's meta-analysis vindicated this hypothesis. Here's a graphic that helps us understand what exactly common factors research and Bruce Wampold's research is all about. This is the results of his meta-analysis. The yellow circle at the top left, let's look there first. So the yellow circle represents the reasons why clients change. In other words, what factors cause a positive outcome to happen or not happen? What are the reasons why clients change? What Wampold found, once he controlled for things like allegiance bias, was that 87% of the time, the client or extra therapeutic factors were the reason for change occurring. So things like the client having things come up in their life and not being able to attend therapy. So weddings, for example, or funerals, or a job loss, or moving to a different part of the country, or whatever. Or it could even be things like the client's motivation level, or their psychological mindedness, meaning their ability to self-reflect. Those kinds of things impact how successful therapy is going to be much more than anything the therapist does. In fact, look at the percentages there. 87% of the reason why therapy is effective is grounded in the client, is the responsibility of the client, not of the therapist. This is quite a sobering reality for us as therapists, because a lot of our research, a lot of our coursework has to do with what we need to do with the client rather than what the client is doing to themselves. And I think over time we're going to see probably a paradigm shift in terms of moving towards more client-centered approaches. But anyway, so of the 13%, the treatment effects, the things that we can control, the largest impact of what we do is therapist effects. That's 46 to 69% of that 13%. Okay, so that big bubble you see in the middle of the screen, the big circle, is representing that kind of small light blue circle within the yellow circle in the top left. So we're just really explaining just that small little sky kind of light blue circle in the yellow circle. Of that, the therapist effects are 46 to 69%. So that's who you are as a therapist, your personality, how warm and likable you are, how flexible you are. Next we have alliance effects. Alliance effects are basically the therapeutic relationship, and more specifically what's known as goals consensus or collaboration. So your ability to form comparable goals with the client and to work towards those goals together, and for the client to achieve those goals. After that we have expectancy or allegiance. This is very important. This has to do with your belief in what you're doing and the theory and intervention you're using, and the client's belief in the theory and intervention that you are using. We call this allegiance and expectancy because the therapist has to have an allegiance to the therapy they're providing, believe in it, and the client has to have expectancy of change occurring, in other words, belief that the intervention is going to be successful. Okay. After that, we have feedback effects. Feedback effects are the ability of the counselor to ask the client what is going well and what can be improved, and to adjust or modify treatment based on the feedback that they get from the client. This can prevent premature termination. The client declining in treatment can be very important to do, and we'll be learning more about this as we go through this course. Finally, we also have model and technique. That's the very last piece to this puzzle, and this is only 8% of that 13%, that tiny green dot. Model or technique represents the difference between theories, and it is incredibly small in the context of everything else, basically, that we've been looking at. It's the smallest factor of all of the ones that we've just mentioned. So if you want to understand what, the impact of what we can control for, things like the therapist and the alliance, expectancy and allegiance, model and technique, we can do a little bit of basic math to explain that 13%, to break it down. So let's say the therapist accounts for 46 to 69% of that 13%. That results in about 6 to 8% of the reason for change occurring. The alliance, 38 to 54% of 13%, represents about 5 to 7% of the reason why change occurs. Expectancy and allegiance is 30% or more of 13%, and that represents about 4% or more of the reason why change occurs. And model or technique, 8% of 13%, represents, and get this, 0 to 1% of the reason why change occurs. In other words, whether you choose CBT or psychodynamic therapy or solution-focused or person-centered, really doesn't matter. 0 to 1% impact compared to everything else we've talked about, but especially the client. Now you may wonder, if you're a math kind of person, if you add all those numbers up, they don't add up to 13% exactly, and that's because, if you recall from our earlier graphic, some of those circles basically had shared variance with each other. They weren't separate. You can't really separate out things like, for example, expectancy and allegiance with model and technique, because it is the client's belief in what you're doing and your belief in what you're doing that really matters, and so it's quite hard to separate out those and say they are separate individual variables. So here's a simpler graphic that I think better represents what really causes change to occur, and this is all based on the findings from meta-analysis. In the blue we have the client. You'll notice that this is the vast chunk of the pie, 87%. The therapist is next as the red slice, the alliance, the green, the allegiance and expectancy, belief in change occurring, is purple, and the thin blue sliver is model and technique. So, we just learned about group differences, effect size, and meta-analysis. And that concludes this video lecture.